Section 7.3. Double columnar transposition. As the name implies, double columnar transposition means doing two columnar transpositions in succession, preferably with two different keys. This eliminates the possibility of matching strips. Remarkably, a general solution was found in 1934 by Solomon Kullback and published by the Signals Intelligence Service. The 31-page book was declassified in 1980 and published by Aegean Park Press. Aegean Park Press was for many years an invaluable resource for books on cryptography. It went out of business sometime after 2001, when Wayne G. Barker, its founder, died, and the books became unavailable. I'm happy to say that www.openlibrary.org now has these books, accessed July 2019. I will not repeat Kullback's analysis here, except to say that it is based on determining where each plaintext letter will occur in the ciphertext. Instead, I will discuss three methods for defeating Kullback's solution. By the way, Kullback went to the same high school as my father, but 6 years earlier. One simple method is to change the shape of the grid by blacking out a few squares. These squares could form a rectangle or some other shape in one of the corners or even in the middle of the grid. Here are some examples. The blacked-out sections can have different sizes, shapes or locations for each of the two transposition steps. The size, shape and location of the blacked-out sections can be appended to the key so that a different blackout is used for each message. Double columnar transposition is rated 4. Double columnar transposition with blackouts is rated 5. The opposite method, called null block, is also effective. You can insert a block of null characters into the intermediate ciphertext or the final ciphertext, or both. It is not helpful to add the null block to the plaintext. The size and location of the block can be specified by a numeric key. These should be varied from message to message. Combining any transposition cipher with any substitution cipher strengthens both. Double columnar transposition combined with simple substitution is rated 6. Double columnar transposition combined with a general polyalphabetic substitution is rated 8. Section 7.4. Cycling columnar transposition. Another variation on columnar transposition is cycling columnar transposition. It comes in two flavors, horizontal cycling and vertical cycling. Horizontal cycling requires two keys, one for cycling the rows and one to determine the column order. Begin by writing the message into a rectangular block left to right across the rows. Next, write the cycling key vertically to the left of the rows. If there are more rows than the length of this key, repeat the key as many times as needed. If the cycling key is a word or phrase, convert it to numbers in the usual way, using alphabetic order. Once the cycling key is in numeric form, cycle each row left by the number of positions indicated. Then read out the letters vertically in the order specified by the column key. Here is an example using the cycling key Cycles and the column key Paul Revere. The same method of matching up paper strips that was used to solve the columnar transposition still works for the cycling columnar transposition. It is only slightly harder because the last letter on each row is adjacent to the first letter, potentially forming a low-frequency bigram. This is at most a minor impediment to Emily. Columnar transposition with horizontal cycling is rated 3. Vertical cycling is similar. Instead of cycling rows of the block left, you cycle the columns of the block upwards. Here is an example using the keyword cycle for cycling the columns and the key phrase Paul Revere for selecting the order in which the columns are read out. This cipher can still be solved by matching up paper strips, the same as a regular columnar transposition, but Emily will need 2 strips for each column, one for the top section and one for the bottom. When each column is cycled, some of the characters from the top of the column are moved to the bottom and become the new bottom section. The remaining letters move upward and become the new top section. In the example, the left column ODYTEL moves up one position, so DYTEL becomes the new top section, and O becomes the new bottom section. These sections still need to be on separate strips because Emily does not know whether these letters came from a long column or a short column. This makes the matching process considerably harder. Columnar transposition with vertical cycling is rated 4. It is feasible to perform both vertical and horizontal cycling on the block. This is comparable in strength to double columnar transposition. Remember, though, that the more complex you make your cipher, the more time it takes and the more difficult it is to both encipher and to decipher accurately. Double cycling columnar transposition is rated 5. Section 7.5. Random number transposition. Let's look at an entirely different type of transposition. This transposition does not involve any sort of array or grid. Instead, it simply numbers the letters in the message randomly. You can use any random number generator. There are several presented in Chapter 13. The only random number generator I have described so far is the chained digit generator in Section 4.5.1, so let's use that generator to illustrate. Generate one random digit for each letter of the message, like this. First, take all the letters numbered 1 going left to right. These are C, V and I. Now take all of the letters numbered 2. These are A, O and L. Then take all of the letters numbered 3, namely N, E, E and M. Continue this way until all of the letters have been taken. To decipher this message, Riva would first generate the random digits. There are 3 ones, so she would write the first 3 letters of the ciphertext CVI under the 3 ones, like this. Riva would write the next 3 letters of the ciphertext AOL under the 2s, like this. And so forth. Random number transposition is rated 4. It can be broken by trying all possible seeds for the random number generator. The cipher can be strengthened by using a longer seed or by selecting letters from the plain text using the 10 digits in an order other than 1, 2, 3. This is equivalent to applying a simple substitution to the outputs of the random number generator. For example, if you wanted to start with the letters marked 4, then you would change all the 4s into 1s. If you wanted to take all of the letters marked 7, you would change all 7s into 2s, and so forth. Then you proceed as described. This increases the number of possible keys by a factor of 10, or 3,628,800. With this improvement, chained digit transposition is rated 5. For a computer version, where the random number generator produces random bytes, the method is rated 7 because there are so many possible orders for rearranging the 256 different bytes. Section 7.6. Selector transposition. Since we are looking at random numbers, let's look at a different transposition cipher based on random numbers, namely a selector transposition. The idea is to break the message into roughly equal pieces and then to merge those pieces using the random number sequence. Suppose the plain text has 100 characters and you want to split it into 3 parts. Assume you have a random number generator that produces the digits 0, 1 and 2 with equal probability, and that you have chosen a seed which acts as the key for the transposition. You need to know how big to make each part of the message. This is easily done. Just generate the first 100 random digits and count how many of each digit are produced. Say there are 36 zeros, 25 ones, and 39 twos. You would slice the message into 3 pieces: P0 with 36 letters, P1 with 25 letters, and P2 with 39 letters. Enciphering is easy. Each time the generator produces a 0, take the next letter from P0. Each time the generator produces a 1, take the next letter from P1. Each time the generator produces a 2, take the next letter from P2. Deciphering is even easier, because Riva does not need to know how large each piece had been. Each time she gets a 0, she puts the next letter into P0. Each time she gets a 1, she puts the next letter into P1. Each time she gets a 2, she puts the next letter into P2. Then she concatenates the 3 pieces, or she simply reads the message, ignoring the line breaks. When this is done with only 2 pieces, it is trivial for Emily to reconstruct the message. The rating is 1. With 3 pieces, it is a bit harder and the rating is 2. With 20 or more pieces, the rating is 5.